Here is a combined summary of the 2 pages. The paper presents a novel end-to-end framework for closed-form computation and visualization of critical point uncertainty in 2D uncertain scalar fields. Critical points are fundamental topological descriptors used in the visualization and analysis of scalar fields, but uncertainty in data creates uncertainty regarding critical point positions. The proposed framework addresses this challenge by deriving critical point uncertainty in closed form, accelerating critical point probability computations using a parallel implementation with the VTK-m library, and demonstrating integration with the ParaView software system. The paper highlights the importance of quantifying and visually conveying uncertainty in critical points to prevent misinformation in topological visualizations and analysis. Previous studies have investigated uncertainty in critical points arising from uncertain scalar fields, including modeling noise in data with multivariate Gaussian distributions and deriving critical point probabilities using Monte Carlo sampling. The proposed framework contributes to the field by analytically deriving the critical point probability per grid position in a regular grid for independent parametric and nonparametric noise models with finite support. The framework enhances the efficiency of results compared to Monte Carlo sampling and provides more robust results compared to multivariate Gaussian and other parametric models. The paper also discusses related work in uncertainty visualization, including techniques for portraying uncertainty in scalar, vector, tensor, and multivariate data. Various noise models have been previously explored, including statistically independent Gaussian and uniform distributions, multivariate Gaussian noise models, and nonparametric models such as histograms and kernel density estimation. The paper proposes a novel end-to-end framework for uncertainty visualization of critical points in 2D uncertain scalar fields, which comprises a threefold contribution. First, it derives critical point uncertainty in closed form for parametric and nonparametric models with finite support. Second, it accelerates critical point probability computations using a parallel implementation with the VTK-m library. Finally, it demonstrates integration with the ParaView software system to demonstrate near real-time results for real datasets. This research paper proposes a novel approach to compute the probability of a point being a local minimum, local maximum, or saddle in uncertain scalar fields. The uncertainty is modeled as probability distributions at grid vertices and their neighbors. The method considers 4 neighbors of a domain point along the 2 coordinate axes directions in a regular grid to compute the probability of the domain point being critical. The paper defines a point as a local minimum, local maximum, or saddle based on its function value relative to its neighbors. The probability of a point being a local minimum, local maximum, or saddle is computed by integrating the joint probability distribution of the random variables at the point and its neighbors. The approach is first described for the 1D case, where the probability of a point being a local minimum is computed by integrating the joint probability distribution of the random variables at the point and its 2 neighbors. The integral is simplified into 3 types of integration templates, depending on the number of intervals overlapping with the piece of the outer integral range. The method is then generalized to the 2D case, where the probability of a point being a local minimum is computed by integrating the joint probability distribution of the random variables at the point and its 4 neighbors. The approach comprises 3 main tasks: determining the pieces of the outer integral range, computing the integration for each piece, and summing the integrals to compute the local minimum probability. The paper also provides an illustration of the method for computing the local minimum probability, showing how the pieces of the outer integral range are determined and how the integration is computed for each piece. The time complexity of the approach is linear with the number of input intervals. Overall, this research paper presents a novel and efficient approach to compute the probability of a point being a local minimum, local maximum, or saddle in uncertain scalar fields, which has applications in various fields such as computer vision, robotics, and scientific computing. Local maximum probability and saddle probability calculations in 2D and 3D domains. In the context of critical point probability computation, the local maximum probability at a domain point P can be calculated by computing the probability of x1 being greater than x2 and x3, equivalent to computing the probability of x1 being less than x2 and x3. This can be achieved by applying the local minimum probability computation algorithm to negated random variables x_1 equals x1, x_2 equals x2, and x_3 equals x3. Saddle probability, on the other hand, is computed by integrating the joint probability PDF_joint over its support where the random variable x1 is simultaneously smaller than x2 and greater than x3. Mathematically, the saddle probability can be represented as the sum of two terms. T1 equals PR, x1 less than x2, and x1 greater than x3, and T2 equals PR, x1 greater than x2, and x1 less than x3. The term T1 can be computed using the core integration formula, which involves integrating PDF_joint over the support of x1, x2, and x3. Extending these calculations to the 4D domain, local minimum probability in the 4-pixel neighborhood case can be computed using a similar core integration formula, which involves integrating PDF_joint over the support of x1, x2, x3, x4, and x5. Saddle probability in the 4-pixel neighborhood case can also be computed using a similar approach, with the core integration formula involving the integration of PDF_joint over the support of x1, x2, x3, x4, and x5. Parametric noise models, including uniform and Epanechnikov distributions, are also derived for critical point probability computations. These distributions can be plugged into the integration formulae for critical point probability computations, allowing for the computation of local minimum probability, local maximum probability, and saddle probability. For nonparametric noise models, a histogram with a user-specified number of bins is used to derive critical point probabilities. The histogram can be considered as a weighted combination of non-overlapping uniform distributions, allowing for the computation of local minimum probability, local maximum probability, and saddle probability. A semianalytical solution is also proposed, which provides an approximate but reliable solution at a greater speed. This solution involves drawing samples from the PDF_x1, x1, at a point P and computing the probability of each sample being critical in closed form. The critical point uncertainty code is integrated with the VTK-m software, allowing for embarrassingly parallel computation and optimized access to neighbors. This integration enables significant speedup in critical point uncertainty computation on various architectures, including AMD, NVIDIA, and Intel processors. Here is a combined summary of pages 7 and 8 of the research paper. The authors present a novel approach to computing critical point probabilities in topological data analysis, TDA, using closed-form computations. They demonstrate the correctness and enhanced performance of their proposed method compared to the Monte Carlo (MC) sampling approach. The results show a 64 times and 119 times speedup for local minimum and saddle probability computations, respectively, with a comparable accuracy. The authors also compare parametric and nonparametric noise models for computing critical point probability. They use a synthetic dataset modeled as a Gaussian mixture model and apply various noise models, including uniform, Epanechnikov, Gaussian, and histogram models. The results demonstrate that the Epanechnikov model provides a good balance between accuracy and performance, while the histogram model exhibits the most robustness to outliers. However, the histogram model is computationally expensive and is mitigated by a semianalytical solution that reduces the computation time while maintaining comparable accuracy. The authors also apply their proposed algorithms to real-world datasets, including climate data and oceanology data. For the climate data, they visualize the mean sea level pressure variable simulated from the Energy Exascale Earth System Model, E3SM, and study the uncertainty of critical points in decompressed data using the MGARD compressor. They utilize the error bound to derive critical point probabilities and visualize the results using a height field. For the oceanology data, they evaluate the quality and performance of parametric and nonparametric noise models for the Red Sea ensemble simulations. The results are visualized using spherical glyphs in ParaView to identify positions with high probability. The authors implement their algorithms using a C++ parallel implementation with VTK-m, which enables them to accelerate the computation on various platforms, including serial processors and AMD and NVIDIA GPUs. They report significant speedups, including a 411 times speedup for the climate dataset and a 1646 times speedup for the oceanology dataset. The algorithm presented in this research efficiently computes critical point probability in closed form for both parametric and nonparametric uncertainty models with finite support. This method demonstrates enhanced accuracy and performance over classical Monte Carlo sampling. The proposed nonparametric histogram model shows greater resilience to outliers compared to parametric models, as observed in synthetic experiments. The algorithm integrates with the VTK-m library to accelerate performance using serial, AMD, and NVIDIA backends. Seamless integration with ParaView is also achieved, making the algorithms accessible to a wide audience. Practical utility is shown through application to climate and oceanology datasets. The research highlights the importance of considering spatial correlation in uncertainty quantification. The independent noise assumption can lead to overestimation of probabilities, as demonstrated in previous studies. However, accommodating linear or nonlinear correlations increases the sensitivity of results to outliers. Further research is needed to derive closed-form solutions for critical point probability computation that can accommodate spatial correlation and are robust to outliers. The study also notes that the quality of results strongly depends on how well the application can provide upper and lower bounds for the values at a grid point. The proposed nonparametric models can mitigate the effects of overestimation or coarseness of bounds resulting from outliers by assigning a lower weight or probability to outliers. Limitations of the work include the assumption of finite bounds for uncertainty at each grid point and the independent noise assumption. Future work aims to extend the algorithms to more neighbors and 3D datasets, and to investigate uncertainty in other topological visualizations, including contoured trees and persistence diagrams. The research utilizes sphere glyphs and height maps for visualization, but further study is needed to evaluate the perceptual quality of these methods and possibly derive new rendering techniques. The study demonstrates the effectiveness of the proposed algorithms through enhanced accuracy and performance over classical methods, and highlights the importance of considering spatial correlation and outliers in uncertainty quantification. The research contributes to the advancement of topological visualization and uncertainty quantification, with potential applications in various fields, including climate science and oceanology. This research paper presents a comprehensive review of uncertainty visualization in scientific computing, focusing on the visualization of uncertain scalar fields and vector fields. The authors provide an extensive bibliography of 70 references, covering various aspects of uncertainty visualization, including probability density function estimation, critical point analysis, and visualization techniques for uncertain scalar and vector fields. The paper begins by discussing the importance of uncertainty visualization in scientific computing, highlighting the need to quantify and visualize uncertainty in data to facilitate informed decision-making. The authors then provide an overview of probability density function estimation methods, including Parson windows and Gaussian mixture models. The subsequent sections delve into critical point analysis, discussing the importance of critical points in understanding the behavior of scalar fields. The authors present various methods for computing critical points, including the marching squares algorithm and the topological analysis of ensembles of hydrodynamic turbulent flows. The paper also covers visualization techniques for uncertain scalar and vector fields, including isosurface rendering, volume visualization, and glyph-based visualization. The authors discuss the challenges of visualizing uncertainty in high-dimensional data and present various approaches to addressing these challenges, such as dimensionality reduction and feature-based visualization. Furthermore, the authors explore the application of uncertainty visualization in various fields, including medical imaging, fluid dynamics, and climate modeling. They highlight the importance of uncertainty quantification and visualization in these fields, where accurate predictions and decision-making are critical. The paper concludes by discussing the limitations and future directions of uncertainty visualization, including the need for more efficient algorithms, improved visualization techniques, and increased adoption in various fields. In summary, this paper provides a comprehensive review of uncertainty visualization in scientific computing, covering probability density function estimation, critical point analysis, and visualization techniques for uncertain scalar and vector fields. The authors highlight the importance of uncertainty visualization in various fields and discuss the limitations and future directions of this research area.